A massive volcanic eruption occurred 640,000 years ago in Wyoming's northwest corner in the middle of Yellowstone National Park. As a result, a bubbling caldera is formed there. The caldera's 3,472 square mile park is filled with geological wonderlands such as erupting geysers and bubbling pools. These features are ultimately driven by magma and superheated fluids churning beneath the rock's surface. One of these regions, known as the Norris Geyser Basin, is located northwest of the caldera and contains over 500 different hydrothermal features. These raging geysers and pools are constantly changing daily. Still, a much more significant change has also occurred. For more than 2 decades, an area larger than Chicago and centered near the basin has experienced irregular bursts of inflation and deflation of several inches in size. It can be hard to pinpoint the exact causes of a particular movement in a volcanically active region like Yellowstone. However, a recent study published in the Journal of Geophysical Research, Solid Earth, might help explain why this particular patch of land has been breathing in and out. Daniel Zurison, a research geologist at the U.S. Geological Survey's Cascades Volcano Observatory, and also one of the study's co-authors, stated that it is very likely that Norris has been a center of deformation for a very long time. Scientists used decades of satellite-based radar and GPS data from the area to model what might have happened beneath Norris Geyser Basin's surface based on these changes. The late 1990s saw the intrusion of a magma body beneath Norris. Simultaneously, fluids trapped within the magma began to bubble out and make their way through the rocky maze above them. The ground would inflate if the fluids could not move and pressure continued to build. The ground, on the other hand, would deflate if they're able to move to another location. Magma-derived fluids can still be found near the Earth's surface today, just a mile or so below the surface. To be clear, the new research does not imply that the supervolcano that formed Yellowstone's caldera and last erupted 640,000 years ago is any more likely to erupt now than it was previously. Instead, these geological movements may help explain why the world's tallest active geyser, the Steamboat Geyser in Yellowstone National Park, has been erupting at a record-breaking rate since March 2018. The researchers also hypothesized that the changes below Norris may indicate a slightly increased likelihood of hydrothermal explosions occurring in the basin. Yellowstone's geology is notoriously difficult to decipher, making subsurface exploration one of the park's most difficult aspects to study. Researchers agree, however, that a large body of magma being injected into the ground, as well as fluids escaping during the event, are both plausible explanations for the rising and falling ground. Michael Poland, the chief scientist at the U.S. Geological Survey's Yellowstone Volcano Observatory, says that we might only just be beginning to understand how dynamic Norris Geyser Basin is. Thermal features dating back 115,000 years have been discovered in Yellowstone National Park's notorious Norris Geyser Basin. This makes it the oldest thermal area in Yellowstone. It's also the hottest, with temperatures reaching 459 degrees Fahrenheit, approximately 1,000 feet below the surface. This boiling region of Yellowstone is home to the Steamboat Geyser, which demonstrates how drastically and unexpectedly the area can change. The geyser, which stands 400 feet tall, has a history of infrequently erupting, with time intervals between major eruptions ranging from 4 days to a half-century. However, since March 2018, Steamboat has shown signs of life as frequently as once per week. Its 32 eruptions in the year 2018 set a record that was broken in 2019 when the geyser erupted 48 times. Helen Robinson, a geothermal specialist at Glasgow University who was not involved in the new research, said that this blinking thing could just have gone crazy when she saw the results of the experiment. Although the public's attention has been drawn to the mercurial geyser's hyperactivity, scientists are more interested in the basin's dramatic quavering. Between 1996 and 2004, the elevation of an 18-mile-long region increased by 4.7 inches, but then decreased by 2.8 inches between 2005 and 2013. This region then began to rise at a rate of 5.9 inches per year between the end of 2013 and the beginning of 2014, the fastest rate of uplift ever observed within Yellowstone National Park. The seemingly unstoppable uplift came to a halt in March 2014 when a 4.9 magnitude earthquake rocked the Norris Geyser Basin. After years of gradually sinking and rising, the ground finally began to sink again in early 2019. However, the basin is now approximately 5 inches higher than it was in 2000. The Norris Geyser Basin's deformation was tracked using satellite radar and GPS data. and geologists believe the upheaval began when magma rose just under 9 miles beneath the Earth's surface between 1996 and 2001. The Norris Mammoth Corridor is a series of faults and vents that run through the area just outside the northwestern rim of the supervolcano's youngest caldera, and this corridor is the one that leads to the basin. The magmatic intrusion caused the uplift event that occurred between 1996 and 2004, and as the magma cooled, the dissolved fluids were able to bubble out. This process reduced the magma body's internal pressure, causing it to deflate like a balloon with a hole in it. This most likely resulted in another drop in ground level between 2005 and 2013. Because the escaping fluid became repeatedly trapped in pockets beneath layers of rock, the ground has been gradually creeping upwards ever since. Scientists have struggled to identify and document the cycle of magmatism and hydrothermal activity. Robinson hypothesizes that fluids other than magma may collect in pockets and occasionally escape elsewhere as the landscape inhales and exhales. Heavy snowfall in recent years is one possible example. There are geysers and the possibility of explosions on the planet's surface. The group believes that magma-derived fluids are resting just beneath Norris Geyser Basin's surface. All over the region, hydrothermal explosion craters dating back thousands of years can be found. These craters were formed by geologic pressure cookers of confined, scorching water, which rapidly lose pressure and flash boil into steam if the rock cracks, which again is an unlikely event. These craters can be found throughout the region. Despite the fact that major explosions are extremely rare in Norris Geyser Basin, a new one could occur at any time. If fluids have accumulated near the basin's surface, there is a slightly increased chance of hydrothermal explosions occurring. However, as Zurizen explains, the rocky plumbing networks are extremely complicated. There are always subtle shifts taking place that can either increase or decrease the likelihood of an explosion occurring. The team believes that the possibility of further explosions is extremely remote, and as a result, they do not recommend restricting public access to the area. The team is also curious whether the accumulation of magmatic fluids has anything to do with the recent record-breaking number of eruptions at Steamboat. During the 1960s and early 1980s, the geyser experienced comparable activity increases, possibly related to basin breathing cycles. But if this is the case, it begs the question, why is this particular geyser showing off while others remain silent? Why not Equinus, which is conveniently located right next to Steamboat? The exact link between Steamboat's hyperactivity and the magma intrusion, according to Zurizen, is at best circumstantial. However, the timing does line up. He hopes that in the not-too-distant future, he and his colleagues will be able to investigate the fluids that bubble up through the Earth's surface to see if they have chemical signatures of a magmatic origin. Nonetheless, the fact that researchers were able to create a narrative that could explain these dramatic changes is a testament to the decades of data that have been collected and the modern scientific techniques that have been developed. Such success, according to Zurizen, would have been nearly impossible just 20 years ago.